Swayam Prabha. Digital India. Educated India.
Okay, and if GCD divides a number which is not 0, so if n divides, or let's say m divides n and n not equal to 0, then m is less than or equal to n, absolute values. So this GCD is less than or equal to D. So we have D is less than or equal to GCD and GCD is less than or equal to D. So GCD must be equal to D. Okay, and D is in the set L. So this is the proof that GCD is in the set L, and you should go over that a couple of times to see all the elements fitting together. And there is an implicit inductive argument going on, and it doesn't explicitly do the Euclidean algorithm or refer to it here, but we are using the quotient remainder theorem to invoke the remainder, and so that's similar to what all the elements are going into the Euclidean algorithm. All right, so the bottom line is that we have both these claims, and let me finish off with kind of put them together to actually see what exactly this LAB is now. And here is the theorem says that LAB is exactly all the multiples of GCD of AB. Okay, so it's an element is an LAB if and only if it is a multiple of the GCD of AB. So I'm just defining G as the GCD of AB. So I had to show, take an arbitrary X, and I had to show both directions. The forward direction, if X is an LAB, then G divides X, so was exactly handled in claim 1. So it's the other direction that I want to show, that if I take an arbitrary multiple of G, say G times H, and I want to say it belongs to LAB. Claim 2 gets me pretty close. It tells me that G itself is in LAB. What I want to prove is that any multiple of G is in LAB. But this is essentially because LAB is closed under multiplication. But let me go over that as written here. So I know G is in LAB. So I can write G as AU plus BV. That's the definition of LAB. And now if I consider G times H, it looks like AUH plus BVH, and that is also therefore in LAB. All I did was change this U and V now to UH and VH. So this is basically saying I could take any element in LAB, multiply it by some element H, and I'll still land in LAB. Okay, so this X still stays in LAB. So that's the end of the proof of this theorem here. But the important, more than this fact that LAB is exactly the multiples of GCD of A and B, what you might find yourself using often is this sub claim here that the GCD can be written as a integer linear combination of A and B. Again, this has a name, as I mentioned earlier, Bezout's identity. So this is something we will want to keep in mind. All right, so that's it for now. An important concept for integers is that of prime numbers, and we'll see today this fundamental theorem of arithmetic about prime factorization of integers. So to begin with, what's a prime number? It's an integer which doesn't have any other positive divisors other than 1 and p itself. So 1 and p are always divisors, and we'll just focus on the positive divisors. And as long as those are the only two divisors, then the number is a prime number. And we are not allowing 1 to be considered a prime number when it has only one positive divisor, namely itself. So that's not a prime number in this definition. The smallest prime number is 2. Okay, so yeah, here is a list of prime numbers. It looks like this somewhat random sequence with no easy pattern there. 2, 3, 5, 7, 11. You've seen prime numbers a lot, I'm sure. And the theorem we are going to prove now is that every integer greater than or equal to 2 can be written as a product of a bunch of prime powers. So here each pi is a prime number and di is a positive integer. And not just that you can write them in this way, but it's a unique factorization. So if you up to reordering, so if you insist that these PIs are ordered such that it's an increasing sequence, then there is exactly one such sequence of primes and their powers, which will let you write A as a product of these prime powers. Okay. So this is actually a very, very useful fact. You've seen this in high school, I'm sure, and it goes back all the way to Euclid and old civilizations. Though Euclid himself didn't quite state it this way, but it's pretty much following Euclid's arguments. You can prove this, and we actually already saw that a prime factorization exists. That was one of our examples for strong induction, and it's a pretty easy, fact. Doesn't use anything deep other than things like commutative and associative multiplication, and of course the definition of what it means to be a prime number. So the fact that you can take a prime number and keep factorizing it until you get to a point where you cannot factorize, that's when you get to a point where it's a prime number. And this process will terminate because your factors are getting smaller and smaller. So that is what you could prove just using induction. What we are going to see today is that it's a unique factorization that you'll get no matter how you try to go about finding factors and splitting your number into two parts and then continuing to factorize. What you end up with will be just the same sequence always, right? It's the same. There's only one sequence of prime numbers and their powers that you can use to write this number. Okay, so let's see how we prove it. To prove this, we need like a new ingredient we didn't talk about so far, and that's essentially our first non-trivial fact about primes, and this is called Euclid's lemma. So if a prime number divides a product of two numbers, A and B, then it should divide either A or B. Okay. So if a prime number divides a product of two numbers, it should divide either the first number or the second number, or maybe both. How do you prove this? So we'll consider two cases. Depending on, let's say, depending on whether the prime number divides A or not. So in fact, more precisely, I'm going to state my cases as, so let's look at the GCD of A and P. Okay? Since GCD is a common divisor and P has only two divisors, 1 and P itself. So the GCD has to come from one of these two divisors. So GCD is either 1 or P. And the two cases are therefore if GCD is P, well in this case P divides A and we are done. So we just needed to prove that either P divides A or P divides B. So P divides A, we are done. So the interesting case is when P doesn't divide A, then we'd like to show that it actually divides B. And here we use Bezout's identity from last time. So remember if GCD, that GCD can be written as an integer linear combination of the two numbers. So 1 can be written as an integer linear combination of A and P. So there are two integers U and V such that 1 equals UA plus VP. And then I multiply both sides by b, I get that b can be written as u times a times b plus v times p times b. Okay, so now this AB here is exactly what, so why did I multiply by B? So that I can talk about AB on this side, and AB is something it's a multiple of P, right? That's our starting point. So I can rewrite AB as K times P. And now both these terms have P as a factor, and I can take that out, and therefore I will get that P divides B. Okay? So in this case also I'm done. So I prove that if P doesn't divide A, then P has to divide B. All right, so that's a very easy lemma. How do we use it to prove unique factorization? So I'll actually use a generalization of this lemma, which can be proven using induction, and this lemma for the two products as a two factors A and B as a base case. So the generalization says that if you took a product of n integers instead of 2 here, and suppose P divides their product, then there is someone out here that P divides. So P has to divide one of these AIs. Okay. All right. So that's something you can prove easily by induction and using this as a base case. So I'll leave it to you to think about that. But let me complete the proof of uniqueness of prime factorization now. Okay, so here's the proof. So I'm going to use the well ordering principle to say, let's pick the smallest positive integer. So suppose the uniqueness is not true, then for the sake of contradiction, then there is a non-empty set of integers which have distinct prime factorization. Let's pick the smallest such integer. So let's say z, and it has two distinct prime factorization. Let's say those are p1 to pm and q1 to qn. So here I didn't indicate prime powers because I'm just going to repeat. If I want two copies of p1, I'll just have p1 times p1. So p2 will be equal to p1. And so forth. Right, so I can write z as a product of a bunch of prime numbers, possibly with repetitions. And I can do the same, and it's sorted, say p1 to pm are in increasing order. So not strictly increasing, but increasing order. And suppose q1 to qn is another prime factorization, which is distinct. Okay, so somewhere something is different. Either the numbers, maybe the m and n themselves are different, or maybe they are the same, but somewhere in the sequence there is a difference. Okay. So my first claim is that let's say it's an increasing order, right? So you cannot have PM and PQN be equal. So the maximum among these and the maximum among these cannot be equal. And why is it so? Because otherwise I can cancel. I can do a cancellation. If PM equals QN, I'll do a cancellation. And since these are distinct, I'll still be left with some two things which are distinct, because what I removed were identical. So P1 to PM minus 1 and Q1 to Qn minus 1 would be distinct sequences. And still they multiply to the same value, namely z with a factor p and missing. Right. So that's that. What does that contradict? That contradicts the assumption that z was the smallest positive integer which had two distinct factorization. So I cannot have this. I cannot have the maximum be equal. So they're distinct. And let's say, so one of them is larger than the other. Let's say PM, the maximum on this left is larger than the maximum on the right. So let's say that the maximum is PM. So PM is strictly larger than the maximum here. In particular, it's larger than everyone here. If it's larger than the maximum here, it's larger than everyone there. So PM is greater than QI, strictly greater than QI for all of these Q1 to N. Which means PM, if it's greater than these numbers, it cannot divide any of these numbers. Remember, these are all positive numbers. So their divisors are all less than or equal to themselves. So you cannot have that, PM is a divisor of any of these QI. So PM doesn't divide any of these QIs. However, our lemma just now said that this PM divides, since PM divides Z and Z equals Q1 to Qn, the lemma said that PM has to divide some Qi. Okay, so that's a contradiction. Here it said PM doesn't divide any of these Qi, and the lemma told us that PM has to divide some Qi. So that's a contradiction starting from the assumption that there is a non-empty set of integers which have two distinct prime factorizations. So that's it. It's a clever argument, but nothing too complicated. Okay. So now that we have this prime factorization, the uniqueness of prime factorization, the moment you get an integer, say a positive integer, you could start talking in terms of its prime factors, and that lets you simplify your view on things we already talked about. So let's just go back and revisit. We talked about divisors, right? And they had this very irregular pattern. What can we say about the divisors? Well, now we can say something about the divisors in terms of the prime factors. So let's say my number A, it's prime factorization. So here, for convenience, I've changed the notation a little bit. So think of this is a product notation. So there's a product over all primes, and for every prime P, I have an exponent here, alpha P, right? So A can be written as P to the power alpha P, product over all P. Of course, there are infinitely many P's, but this product will be only over finitely many of them, wherever these alpha P's are positive, right? So there will be only, everywhere else I'm considering alpha P as to be 0. So I can write, I'm just denoting the unique prime factorization of A using these exponents alpha P. And similarly, let the exponents beta P denote the unique prime factorization of B. And the divisibility, or the definition of A divides B can now be equivalently understood as, for A to divide B, each of these alpha P's, for every P, alpha P has to be less than or equal to beta P. Okay, and it's not very hard to see that if in both directions, right? If A divides B, then by definition B is equal to A times Q for some Q, which it's some integer Q, which itself can be prime factorized. So let gamma P denote the exponent of P in the prime factorization of Q. And so now we just do some arithmetic to say that, look, if B equal to AQ, here every prime P has an exponent beta P, and here it has alpha P and gamma P for the same P. And since it's unique, the only way this can, this factorization is unique, they have to be the same, right? So the exponent beta P here should be equal to the exponent you get here for P, namely alpha P plus gamma P. So everywhere this has to happen, which means, and gamma P is a non-negative number. So alpha P plus gamma P is at least alpha P. So it means that beta P is at least alpha P. And the reverse direction is very similar. And if you assume that alpha P is less than or equal to beta P everywhere, that gap between them I define as gamma P. It's non-negative gamma P, and I use that to define Q, and then I can conclude that B is equal to A times Q. Q makes up for the deficiency in the exponents. So again, A divides B. So if B equal to AQ, then that meets the definition of A divides B. Okay, so that's a it's a pretty convenient way of thinking about divisors. So divisors of B are obtained by picking exponents for each of its prime factors, where that exponent should be no more than its own exponent, no more than B's own uh, exponent in its prime factorization for that prime. We talked about common divisors and GCD earlier. So again, you can look at it in terms of prime factorization, and things are somewhat simpler to see. So here is kind of so we talked about Euclid's algorithm for finding GCD. Here is an alternate algorithm, not particularly efficient, but it's still an algorithm for finding GCD of two numbers. But to start off this algorithm, you need to factorize A and B. You need to find a prime factorization of A and B. From our theorems, and their proofs, we know you can do it, even though not very efficiently. So you can, suppose you're given the prime factorization of A and B. The plan now is to, quickly figure out the prime factorization of the GCD of A and B. And from that, you can multiply them together and get the GCD itself. So how do you find the prime factorization of GCD of A and B? It's pretty simple. For every prime p, as before, let alpha p and beta p be its exponents in the factorization of A and B. In gamma p, so for the prime factorization of GCD, I have an exponent gamma p, which is simply the minimum of the two exponents alpha p and beta p. Okay, so here is an example. Suppose my numbers are 2520 and 3300, which have these factorizations. Then to find the factorization of their GCD, for each prime number, I pick the smaller exponent. So for 2, the smaller exponent is 2. For 3, the smaller exponent is 1. For 5, the smaller exponent is 1. For 7, the smaller exponent is 0. It doesn't occur in one of them. And similarly for 11, the smaller exponent is 0. It doesn't occur in the other numbers. So 7 and 11 don't show up in the GCD's prime factorization. And that's it. That's the GCD, right? This number here, 60, would be the GCD. And here is a visualization of this prime factorization. So the number 3300, its factors I wrote down in such a way, each copy of 2 shows up as a different number here. So I have 2 copies of 2 inside the factorization of 3300. So let's think of it as the first copy of 2, second copy of 2. And for 2520, there are 3 copies. So it needs the first copy of 2, second copy of 2, and a third copy of 2, which will be outside the factorization of 3300. And similarly, say 5, there are 2 copies for 3300, only 1 copy for only the first copy for 2520. So, all these things are the factors of 2520. All these are the factors of 3300. And the ones at the intersection are the prime factors of their GCD. Okay. All right. So, so that's, that would look like a pretty easy way to compute the GCD. However, it's not at all practical compared to Euclid's algorithm, which is actually very efficient, because prime factorization is not easy. You might think it's pretty easy. You can unroll the induction, and that is true, but the number of steps you take is as big as the number itself. It's like it will take at least as much time as counting up to the numbers, a number, to prime factorize it in that way. And that is pretty inefficient. Counting to a 10-digit number would take about 10 to the 10 number of steps, and that is pretty high. And as of course the number of digits grows, the time taken grows grows exponentially. Whereas in Euclid's algorithm, we'll see later, it's pretty, it's proportional to the number of digits rather than exponential in the number of digits. So Euclid's algorithm is way more efficient than, doing this prime factorization first, and then carrying out the GCD computation, which itself is pretty fast. It's also a good time to look at another related concept. Instead of common divisors, we could also talk about common multiples. So, C is a common multiple if both A and B are divisors of C. So C is a multiple of A and C is a multiple of B. And here, an interesting quantity to define is the least common multiple, or LCM of A and B. It's defined to be, it's defined for as long as, so remember GCD was defined for all pairs other than 0, 0. Here it's defined only when both A and B are non-zero. We allow them to be negative, but you could always think of them, A and B being positive if you want. In any case, we define the LCM to be a positive integer. And because we're going to define it as the smallest positive integer, if we think of, if you allow negative integers, then the multiples go all the way to negative infinity. So LCM is the smallest positive integer, which is a multiple of both A and B. Okay, and just like GCD, you can convince yourself that it's well defined because there is at least one common multiple, namely A times B, and further, there's a set. It's a non-empty set, right? It's a it's a set of positive numbers, and it's non-empty. So you can use the well ordering principle if you want to say there is a least element there. In fact, since we have an upper bound on that, one element here, A times B, you can be more precise. You can say this LCM is somewhere in the range 1 to AB. So, here is an example. The numbers are 30 and 36. And here I have actually already written it using prime factors. And so the LCM in this case happens to be 180, obtained by taking the larger of the prime factors in each case. So just to, I'll come back to that in a second. So just like for GCD, we did the, visualized GCD as a tiling. LCM can also be visualized as a tiling. Somewhat differently. So you say you are interested in the LCM of two numbers 8 and 12. Now you think of this as a small tile that is going to be used to tile a large grid. And the large grid is a square grid, n by n grid. And what you're interested in is the smallest square grid that that can be tiled perfectly using this rectangle, 8 by 12 rectangle. Okay, so in this case, there are two copies of 12 along this direction, so that is 24 squares, and this is 3 copies of 8, that is 24. So 24 is the smallest n, which such that n by n square could be perfectly tiled using your 8 by 12 grid. So 24 is LCM of 12 and 8. Going back to thinking in terms of LCM from factorization, it's very similar to what we did for GCD. Given factorization of the two numbers A and B in terms of alpha p and beta p, which are factorizations of some numbers A and B, the exponents of each prime number p in the factorization is a maximum of the two. Okay, so going back to our example, earlier example, now the LCM has for the prime number 2, the exponent is 3, the maximum of this, and here it's the maximum is 2, here the maximum is 2, and here the maximum is the maximum of 1 and 0, so which happens here also the maximum is 1. so maximum point 0. In terms of this Venn diagram, it's essentially the union of everything you see here. And that is the those are the prime factors of the LCM. And again, this is only, it's not very useful as a practical way of doing it because you don't have an easy way to come up with the factorization. But the algorithm for computing, an efficient algorithm for computing LCM can be based on this identity here, which just says that if you took the product of the GCD and the LCM, you'll get the product of the two numbers themselves. And that's not very hard to see if you think in terms of this Venn diagram. So I would leave you with that to reason as to why this would hold. But once you have this, and we already have an efficient algorithm for computing GCD, namely Euclid's algorithm, and division is also something that you can do more efficiently than the naive division algorithm we talked about. Right? That's again an inefficient algorithm, this subtracting one at a time. But your high school division algorithm is an efficient algorithm, so you can use that to compute LCM efficiently. All right, so I'll leave you with the, try to see why this identity holds.